What the heck is calculus? We've all dealt with functions and lines, right? Well, calculus is just an extension of that. Where algebra deals with steady change, calculus deals with changing change. It's more real and exact than algebra and is used throughout math and science. Between 1665 and 1667, at the ripe old age of 22, Sir Isaac Newton discovered and refined calculus at the rate at which college undergraduates learn it. Gottfried Wilhelm Leibniz also independently discovered it, but Newton holds the most credit. In 1666, Isaac Newton was sent home from Trinity College in London on account of the plague. In his spare time, he developed calculus so that he could solve physics problems. These problems were directly represented in the real world, and therefore they weren't clean-cut, and so he needed more exact methods. He answered two fundamental questions. How do we find instantaneous rates of change at a certain point, and how do we find the area under a curve? Two seemingly unrelated ideas which are actually completely linked, that is, by the idea of a limit. Now you may ask, what's a limit? Well, if we ask what is produced at x equals 5 in the function y equals 2x plus 3, where x can't equal 5, then there is no solution. But with a limit, we don't care what actually happens at that point. We are just asking, what does the line approach? So we ask, what is the limit as x approaches 5? And that's y equals 13, this point. So the limit is just the point that is being approached on either side of the line. Now, how do you find instantaneous rates of change? Well, rate is just the change in y over the change in x, but the change at a single point is just 0, so you have 0 over 0, and that's undefined. The way around this is finding the slope of the tangent line to a point on the curve, which is approximate to finding the slope between two points that are really close together. Some might say infinitely close. This is called the derivative. The equation of a derivative is as follows. The derivative of f of x equals the limit as the change in x approaches 0 of f of x plus the change in x minus f of x over the change in x. This is just rate. Change in y over change in x. The difference between the two y's is the change in x, which approaches 0 because we're trying to get the 2 points infinitely close. By the way, the apostrophe beside the f just means the derivative of f. We say f prime. From now on, we're going to call the change in x h. Another notation of the derivative is dy over dx. That would be the noun form. The verb form, or the operator, the thing that is commanding take the derivative of this, is d over dx because it's operating a function f of x which can be written as y. Let's do an example. Say f of x equals x squared. Let's look at x equals 3. Using the formula, f prime of 3 equals the limit as x approaches 0 of 3 plus h squared minus 3 squared over h. The first simplifies to blurb 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 and then blurb blurb blurb, and then f prime of 3 equals the limit as x approaches 0 of 6 plus h. But before we can move on, you have to know this. If something is differentiable at a point, it means you can write the derivative for that point, or differentiate it. For something to be differentiable, it has to be continuous at that point. Now this makes finding the limit as x approaches 0 of 6 plus h much easier. Since it is continuous at that point, the limit is simply the point that would be there if it was continuous, and it is continuous. So you just have to input what x, or in this case, h, approaches, which is 0. So the limit as x approaches 0 of 6 plus h is just 6. But there are actually some shortcuts. The first one, and the easiest one, is the power rule. If we try to take the derivative of the whole function, then we can derive a rule for every single derivative on that line. Say we have f of x equals x squared. We know how to take that derivative. Just input x and you end up with the limit of 2x plus h equals 2x. Now, the proper definition of the power rule is this. When f of x equals x to the n, then f prime of x equals nx to the n minus 1. This means if you give me a function like f of x equals x to the third, then I can take the derivative of any value way faster. All I have to do is turn it into f prime of x equals 3x squared. And bingo, instant derivative. You can find the derivative of any function with some other rules. First, the sum rule. If we have f of x equals h of x plus g of x, then the f prime of x equals h prime of x plus g prime of x. You could think of distributing the derivative operator, d over dx, over the functions. So if we have f of x equals x to the third minus 7x to the fourth, plus 5, then it would be f prime of x equals 3x squared minus 28x to the third plus 0. We just used the power rule to differentiate the first two functions. We can think of each term as a function, or anything in brackets as a whole function, and the derivative of 5 is 0, because if the function is just 5, then that would look like f of x equals 5, or y equals 5, and we know that this is just a horizontal line, and the slope of a horizontal line is 0, and since the slope is constant, that means the derivative of the whole function is 0. So whenever we just have a constant like 5, its derivative is 0. Now the product rule. When f of x equals h of x times g of x, then f prime of x equals h prime of x times g of x plus h of x times g prime of x. So if we have f of x equals this, then h of x equals the x squared, and the g of x equals 3x to the fourth. Then f prime of x equals these plus these. Now this may seem a little bit useless, since you could have just simplified and used the power rule, but for more complex functions that would be a pain to simplify, then you use the product rule and just change its form. For the point of the product rule is to differentiate, not simplify. Now the quotient rule. Well, it's a bit dumb, because instead of telling you about the whole new rule, I'm just going to tell you that you can simply use the product rule instead. All you have to do is turn g of x divided by h of x into g of x times h of x to the negative 1, using basic algebra. Now, the chain rule. The chain rule is all about functions within functions. The chain rule states that if f of x equals h of x, then f prime of x equals g prime of x times h prime of g of x. So if we have f of x equals x to the third plus 5 to the 7th, then h of x is x to the 7th, and g of x is x to the 3 plus 5. Then we substitute it in to the rule, and we get f prime of x equals 3x squared times 7 times x to the third plus 5 to the 6th. And that's differential calculus. Ish. Now, how do we find the area under a curve? The answer is integration. The integral function between two determined points on the x-axis will add up all the rectangles under a curve. These rectangles were imagined by Leibniz to get smaller and smaller and smaller, eventually reaching a limit that when added up equaled the area under the curve. There are two types of integrals, definite integrals and indefinite integrals. The notation for a definite integration is the integral from point A to point B of f of x with respect to x. The a and b points just sets the limit for the integration. The integral that is the inverse of the derivative is the indefinite integral. Also, if you integrate a function, then differentiate the integrated function, you get back to the original function. They are the inverse of each other. This fact is called the first fundamental theorem of calculus. So if you ever want to discover the laws of gravity or general relativity, just call up your new friend, calculus.